Imagine I tell you that sine 30 degree is equal to 1/2. Easy, right? Now let me ask a different question. What is sine inverse of 1/2? Suddenly things become interesting. And here is an even bigger question. If inverse functions reverse a function, then why do we need an entire chapter to define inverse trigonometric functions? Today, we will learn that question and master the foundation of inverse trigonometry. Let's start with something familiar. If f of a equals b, then f inverse of b equals a. In simple words, the inverse function undoes what the original function did. Sounds easy so far. For example, a machine takes 2 and produces 4. The inverse machine simply takes 4 and returns 2. From class 11, we know sine, cosine, and tangent. At first glance, it seems we should simply define sine inverse, cos inverse, and tan inverse. But mathematics doesn't allow us to do that immediately. Something important is missing. Let's look at sine. Sine 30 degrees equals 1/2. But wait, sine 150 degree is also 1/2. And if you keep adding complete revolutions, you will find infinitely many angles whose sine is 1/2. Now think carefully. If I ask for sine inverse of 1/2, which angle should I get back? 30 degrees, 150 degrees, 390 degrees. Mathematics hates ambiguity. An inverse function must return one unique answer. That's where the trouble begins. Here is the golden rule. An inverse function exists only when the original function is one-to-one. Why is it so? Because every output must come from exactly one input. But sine fails this test. Multiple angles produce same value. Therefore, sine is not one-to-one on its entire domain. The same issue occurs with cosine and tangent. So technically, inverse trigonometric functions do not exist yet. But mathematicians found a clever solution. Instead of using the entire graph, we keep only a small portion where the function never repeats values. In that restricted interval, every output corresponds to exactly one input. Now the function becomes one-to-one, and once it becomes one-to-one, its inverse can finally exist. This idea is called domain restriction, and it is the heart of this entire chapter. After restricting the domains, we obtain special intervals called principal value branches. Think of these as official answer zones. Whenever you evaluate an inverse trigonometric function, the answer must come from these intervals. No exceptions. If you memorize only one thing from this chapter, memorize these principal value ranges. They decide whether your answer is correct or wrong. Now, the domains of inverse trigonometric functions. Did you notice something interesting here? The domain of inverse sine and inverse cosine is from -1 to 1. And why is it so? Because sine and cosine themselves never produce values outside that interval. You can never have a sine value equal to 2 or a cosine value equal to -5. That's impossible. So inverse sine and inverse cosine cannot accept such inputs. Let's try to understand this idea of principal value range with the help of an example. We have to find sine inverse of 1/2. Inverse sine asks us which angle has sine equal to 1/2. We know that sine of pi by 6 is 1/2. Now check the principal value range of inverse sine, which is -pi by 2 to pi by 2. Since pi by 6 lies in this interval, it becomes the principal value. Therefore, sine inverse of 1/2 equals to pi by 6. Let's move to the another example. Here we meet an angle whose tangent is -√3. Many students immediately think of several angles. But remember, we only care about the angle lying inside the principal value range of inverse tangent. That's the key idea. We know that tangent of -pi by 3 equals -√3. Now check the principal value interval. -pi by 3 lies comfortably between -pi by 2 and pi by 2. Therefore, it is accepted, and our principal value becomes -pi by 3. Notice that we did not search for all the possible angles. We searched only for angles inside the principal value range. That's the exam trick. Let's check this example. It looks very difficult in first place because it combines three inverse trigonometric functions. Find value of tan inverse of 1 plus cos inverse of -1/2 plus sine inverse of -1/2. This is the exact kind of question students see in boards and competitive exams. The secret is simple. Don't simplify everything together. Evaluate each inverse function separately, then add them. So tan inverse of 1 equals pi by 4. Cos inverse minus 1/2 equals 2 pi by 3. Now you must be wondering, why can't we take 4 pi by 3? Because 4 pi by 3 is outside the principal value range of inverse cosine. Similarly, sine inverse minus 1/2 equals minus pi by 6. Now add these three principal values carefully. After simplification, we get 3 pi by 4. Notice how every step depended on principal values. Without them, we could easily get the wrong answer. Now, let's look at one of the biggest traps in inverse trigonometry. If I ask you to find sine inverse of sine 5 pi by 6, many students immediately cancel sine and inverse sine and write 5 pi by 6. That shortcut is dangerous. Let's see why. First, calculate sine 5 pi by 6. That's equal to 1/2. Now, the question becomes sine inverse of 1/2. We already know the principal value answer is pi by 6, not 5 pi by 6. Why? Because every answer of inverse sine must lie between minus pi by 2 and pi by 2. 5 pi by 6 doesn't belong there. Pi by 6 does. This single idea appears again and again in both exams. Let's now meet one of the most beautiful identities in the chapter. Sine inverse x plus cos inverse x equals pi by 2. Instead of memorizing it blindly, let's verify it. Take x equals to 1/2. Sine inverse 1/2 gives pi by 6. Cos inverse 1/2 gives pi by 3. Adding them gives pi by 2. The identity works perfectly, and you will use this identity extensively in later exercises. Here is one of the most important identities in inverse trigonometry. For any positive value of x, tan inverse x plus tan inverse 1 upon x is equal to pi by 2. Notice the condition carefully. X must be greater than 0. Many students memorize the identity but forget this condition and lose marks in exams. So whenever you see tan inverse x and tan inverse 1 upon x together, first check whether x is positive. If it is, you can directly replace the entire expression with pi by 2. Let's quickly connect the entire story. Inverse function need one-to-one functions. Trigonometric functions are not one-to-one on their complete domains. Therefore, we restrict the domains. This creates principal value branches. Principal values help us define inverse trigonometric functions uniquely. And once you understand principal values, most questions in this chapter become straightforward. In the next video, we will learn advanced properties and exam level questions based on inverse trigonometric functions. See you in the next lesson. If you like the video, please click the like button and subscribe.